Hello, welcome to this solutions guide. This video is intended for students in my AP Chemistry prep class, and this is a hopefully quick video outlining the solutions to the week 1 homework. So in case you wanted to know what you did wrong or how you do some of these questions, here you have it. Quick disclaimer, these questions were on the easier side this first week. If you didn't feel they were easy, then don't freak out, but that is an indicator to you that like, hey, maybe I need to ramp up the study a little bit more. We are still 7 weeks out from the AP exam. So don't freak out. There's still plenty of time to improve your skills and figure out how to do these. So let's get started. Okay, so our first problem is which of the following statements is true about the number of atoms in a 0.50 mole sample of calcium nitrate? So this question is basically about mole to atom conversions or mole to anything conversions for that. So what we do is we have 0.50 mole. And also if you look at the answer choices, this is one of those style of questions where you can't just tell me the answer right away. You have to kind of see which of these actually fits. You have to consider all of them. But what I see quickly is they all discuss the number of atoms of these different elements within the compound. So let's see if we can figure those out and then see if anything matches up with it. So overall, we have 0.50 moles of this calcium nitrate compound. This also allows us to kind of make sure we understand formula units a little bit as well. So it looks like we have one calcium atom in 0.50 moles of the sample. So we're pretty much just going to go 0.50 times 1. I know it's silly to write that out, but there we go. So for calcium, we have 0.50 moles of calcium. For nitrogen, it looks like we have one nitrogen, but hold up. There's this little 2 out there, which represents that there are 2 nitrates bonded to calcium, which makes sense since calcium is a 2+ ion and nitrate is a -1 polyatomic ion. So I'm going to take my 0.50 moles again, times by 2, and I'm going to end up with 1.0 moles of nitrogen. Okay, so hopefully you kind of see where we're going with this. The next one is oxygen, and as you can see, oxygen has 3, but hold up, there are 2 of these nitrate molecules, so technically for oxygen there would be 6 moles for every 1 mole of the compound. So 0.50 moles of the compound times 6 of oxygen, and that's going to give us 3.0 moles of oxygen. Okay, so again, something I wanted you to practice this week and really every week as we do these multiple choice homework questions is doing mental math, being able to do these calculations without a calculator, because the real AP test, you're not going to have a calculator. So all of these should be doable without a calculator. Real quick, if you know anything, hopefully about the mole, you know that 6.02 times 10 to the 23rd of anything, whether that's atoms, whether that's eggs, I don't know, whatever you want, grains of sand. That's how many there are in a mole. So if we have 1 mole of nitrogen, we're going to multiply that by 6.02 times 10 to the 23rd. And we'll get, well, heck, 6.02 times 10 to the 23rd. So right there off the bat, that's our answer. And most of you guys were able to get that. In general, my recommendation is if you get an answer that's you're pretty confident and it's right off the bat, heck, just go with it and maybe star it. And if you have time at the end, you can go back and do the math on all of them and see if maybe the other ones are right, or maybe the first one you did the math wrong, whatever. But if you feel very confident, just bubble in that answer, mark it, and move on. Personally, I recommend when you go through AP Chem multiple choice section, you probably don't want to just see every question once. I'd say you probably want to go through the test 3 times, but we'll talk about that in a future video. All right, so the second question was a chemistry experiment calls for 2 moles of sodium. Which of the following is the best method of measuring the proper amount of sodium? So there is one thing, I guess it doesn't make it 100% clear here, and I'm hoping that's why a few of you missed it, but let's just assume this is like in a chemistry experiment, like at standard conditions, like in the laboratory. So like we're going to assume something close to standard conditions, normal conditions. So in that case, we should know that Na, sodium, is a solid. Now, probably no one told you, oh, you need to memorize which element is a solid, a liquid, and a gas at room temperature. But heck, it's not that hard. Most of them are solids, like almost 90% of them are solids. You've got 2 liquids. So this is a little aside. You got 2 liquids, which are mercury and bromine. And then you have a few gases, which are going to be like oxygen, fluorine, nitrogen, chlorine, hydrogen, and of course your noble gases, like no duh, right? They're called noble gases. All right, so cool. And then there are a few elements that are too unstable to really be able to say what their natural state is. But these are the exceptions. Everything else is a solid. So first of all, knowing that it's a solid, I probably don't want to measure it using a tool to measure volume. That's not going to help me. Another thing is it's going to be really hard to use a balance that measures mass to measure a quantity, which is moles. That's not that good of an answer either. And this one says a volumetric flask to measure the liters. Oh, I don't want to measure volume. That's not the best method right here, especially because it's a solid. I can't make these assumptions that like it takes up a certain amount of space. I don't have any density data, so volume's not really going to be helpful to me. So this does only leave one answer choice left. But if you don't like elimination as your explanation, let's look at the actual answer. Use a balance to measure 46 grams of sodium. Well, first of all, that sounds great because you're actually using a balance to measure mass and not quantity, since you can't do that. And second of all, what's going on here? This gives us a chance to practice molar mass conversion. So if we have 2 moles of Na, so if you're still struggling with dimensional analysis and stoichiometry, check this out one more time to practice. Keep practicing till you get it. Don't give up on this. If you don't understand dimensional analysis and you're just plugging random numbers in your calculator, it is going to eventually come back to bite you in the behind. So we have our initial value, 2 moles of sodium. And whenever we want to convert something or use a conversion factor or some form of dimensional analysis, we want to make sure our units in the top of one fraction and the bottom of the next fraction are the same. So there we go, moles and moles. And we're going to put the unit we are interested in up here, which is grams. Now, a lot of students get confused. How do I know where the moles and the grams go? Well, first of all, let the units guide you so that they cancel out. But second of all, make sure that this value is equal to 1, right? 23 grams, according to the periodic table, of sodium is equal to 1 mole. So we don't write 1 gram is 23 moles. We always want these conversion factors to be equal to 1. So I feel like that goes over a lot of kids' heads, or teachers forget to say it sometimes because it maybe seems obvious to them. But what we're doing is multiplying 2 moles by 1. So it maintains the same thing based on like the identity property or whatever that was from math. And that would give you 46 grams of sodium. So that's our answer. All right, next one. Okay, the next 3 questions are all connected. They use the same piece of data here, which is the molar mass of a compound called styrene. Now, it tells us that the molar mass of styrene is 104.13, and it does tell us the empirical formula, if you can't see that, is CH, and our molar mass is 104.13. Okay, so we reviewed this in class in case you missed it or in case you're still a little bit confused. How do you find the molecular formula if you know the empirical formula and the molar mass? Well, heck, you just take the molar mass of your compound or your molecular formula, since we already know that. Molecular formula is the actual amount of atoms. The empirical formula is just based on the kind of most reduced ratio of the elements involved. So when we divide molar mass of the molecular formula divided by the molar mass of the empirical formula, we will get a value that is essentially sort of like a scale factor of sorts that tells us how many times more the molecular formula has of each atom compared to the empirical formula. So let's write that out. They gave this to us for free, and we can add up the molar mass of the styrene. That's going to be approximately 13.01. So when we plug that in the calculator, we get about 8. So therefore, our answer would be C8H8. We took the empirical formula and we multiplied everything by this multiplier. If you really wanted to double check, you could have gone through and totaled all of these up. I think I threw like a distractor answer in there, but you could also have calculated it that way. So be resourceful. If you were going to default to that of counting them up, I would probably mark this as a like come back later, and whatever you get the right answer, you get the right answer. So that's how we do the first one. The second one is what is the percent composition of styrene? So I don't think we did that much percent comp in class, but here's how you do it. US percent comp is again all about mass. It's not molar composition, it's percent mass composition. So we are going to take the mass of just one element at a time divided by the molar mass of the entire compound. So we could do, since we know now C8H8, we could do all 8 carbons divided by the total molar mass of the compound. But since there is a similar ratio, we can technically use the empirical formula as well. So we're going to do the molar mass of our carbon divided by the molar mass of our formula, which is going to be about 12.01 over 13.01. All right, so I plug that in the calculator and I get 0.923. Now, since there's only 2 elements in this compound, I can probably just subtract this from 100% and it will give me the missing percent. But just in case you want to see it, or if you're working on a problem that has multiple elements in there and you're asked to do mass comp, which there's a short answer at the end of this that's like that, it would be approximately 1.01 over 13.01, and that's going to be just about 0.077. And there we have it. That is our percent composition, as most of you guys were able to solve. So great job. Now, if you did have trouble on these or you are struggling, that's okay, but you've got to practice. Hopefully watching a video like this, going to class, getting other help is going to improve it, but sometimes you just got to practice. So if you are struggling with any specific type of question, feel free to reach out to me. I have lots of practice stuff if you want to put in the time to do it. There's a lot of this, there's no shortcut. It does require a certain amount of practice, even if there are preferred methods or strategies to use. All right, so keep moving. Approximately how many moles are present in a 52-gram sample of styrene? All right, so this is just another molar mass question. They're not going to be this easy on the real AP test. I'm sorry to tell you that, but they are basic skills that you have to master to essentially be able to tackle anything else. Not anything else, but most of the other topics on the test, especially FRQs that love to pull in kind of maybe like an obscure, not obscure, but like a little calculation like this here and there. Okay, so we are going to put grams on the bottom because that's what we discussed before, and we're converting to moles, so we're going to have moles on the top. Again, we want our conversion factor to be equal to 1, which one way to represent that is the molar mass. So we can say 1 mole of styrene is going to be equal to 104.13 based on the data provided in the initial part of the question. And that's going to give us approximately 0.5. So you're like, please don't be this person, the person who's over here on the side of the margins on the AP test, trying to be really specific about the answer, right? They're like, oh my gosh, I got to do this long division. I don't even remember how to do this. Don't be that person, right? Don't fill up half your page in 10 minutes doing a long division. AP doesn't want you to do that. These questions are designed to do without a calculator. So feel comfortable doing this. 50 divided by 100 is going to give you 0.5. Now, if there is answer choices like 0.48 and like 0.54, then yeah, I would also then spend the time doing the long division. But most of the time, there's only one truly reasonable answer, which we'll see in the next question as well. So great job on this. It was 0.5 moles. All right, everybody got it right, but I am going to mention it real quick just for the mental math factor. Okay, so we had this abundance diagram right here, and hopefully most of you guys seem pretty good at reading mass specs now, which is awesome. The mass charge thing, remember we talked about in class, you don't have to really worry about the chance of getting +2 ions and having these weird lagging spikes that are like way down here or way out here or something like that. The AP exam says they aren't going to ask you about ions in a mass spec that aren't at a charge of 1. So the other thing we want to see is, hey, we have this compound, most of it, 80% has a mass of 10, about 20% has a mass of 11. So if we had our calculator, yeah, of course, I'm going to tell you to do this. 10 times 0.801 plus 11 times 0.199. And it's not that hard of a calculation. You would be able to get the answer of the average atomic mass. However, let's practice this mental math thing, right? And what's reasonable and what's not. So first of all, 80.1 AMUs, that's a distractor. That's just in case you don't know how to read the chart. So again, as we move through the class, one of the days we will spend some time looking at all the different types of charts you might encounter, so you do feel comfortable reading it. But let's say you were able to eliminate that one, and now you're like, well, I don't know, it's somewhere between 10 and 11. How the heck am I supposed to figure it out? I guess I'm going to spend all this time doing math. Well, hold up. If it was 50-50, it would be 10.5. And it's not 50-50, so it's not 10.5. It's way more of 10. So your average here is going to be skewed towards the lower number. So the only one that's reasonable is 10.2. 10.8 is on the wrong side of that average, basically. Again, if there was answers like 10.3 or 10.1 or even 10.4, I might feel a little bit more uneasy about making this estimation. But once I start thinking about what's reasonable and what's not, there's really only one good answer here, and that's 10.2, which all of you seem to get. So great job. All right, next one. This is the same type of concept. This is, again, going back to mass spec, isotopes, and atomic weight or atomic mass. So according to the periodic table, the atomic weight of chlorine is 35.45. Based on this information, which isotope is more abundant? Well, we've got Cl35, we've got Cl37. Now, if this was like a 50-50 deal, what would the average be? The average atomic mass would be 36. However, it's not 36. So it's like backwards from the last one. It's not 36. We don't know the percentages, but it's not 36. It's 35.45. It's more in this direction towards Cl35. So then just, even if you haven't taken statistics, just hopefully your math sense over the years has developed enough to the point you're like, well, this is definitely going to be greater than 50, and this is going to be 50 and less. I'm not so sure. Maybe like 75%, 25%. I don't have the exact numbers. We don't need the exact numbers. All you need to be able to do is identify that chlorine 35 is the more abundant isotope because the atomic mass is more skewed towards that one. Now, when you have multiple isotopes, of course, this calculation gets a little bit more tricky, but that doesn't mean that you still can't apply this concept for the most part. Again, when you're doing these practice homework questions, try to do them without a calculator. Actually, do them without a calculator. Don't try. It's better that you get them wrong and practice your mental math a little bit than you're relying on the calculator all the way up to the AP test and then it's not there and you have a meltdown, right? This is more of the type of thing you'll look at. And again, this is something you can do without a calculator. Although this one's a bit more of a stretch, I think, than some of the ones we've looked at before. So let's start rolling with it. Okay, 34.1 gram sample of copper chloride hydrate was heated to drive off the water. The remaining anhydrous sample was 26.9 grams. Which of the following is the number of waters of hydration in the hydrate? So there's a lot going on here. We first need to know what a hydrate is. We need to identify what the formula of copper chloride is. And then we're going to have to also use some mole conversions to solve this. So this is why I mean by it's like a more of a real AP question. They tend to test you on multiple concepts at the same time. So first up, copper C. We haven't talked about this too much in class, but hopefully you have it from your own chemistry teacher. Copper 2 means Cu2 plus, and chloride, you should know it has a -1 ion typically. So when we do our little crisscross thing, if you don't know what I'm talking about, if we are going, we can think about it like as when we balance the formula so that its negatives and positives are balanced out, we get CuCl2 for copper chloride. Okay, so what are we going to do with that? And what the heck is a hydrate? So usually a hydrate's written something like this, some number here, and then it says H2O. And what this basically represents is that this copper chloride molecule is typically found in its hydrate form with a certain number of water molecules around it. This is very common for a lot of compounds. And you'll notice when they mention anhydrous, that means that all that water has been evaporated. It's no longer has this hydrate form. It's just pure copper chloride. So if you've never heard of that, well, you just heard about it. And this is essentially one of the main ways the AP likes to test the concept of impurities or mixtures, because essentially it sort of is. So what are we going to do with this? Well, to solve for this X value, we're basically finding a coefficient. And coefficients, just like subscripts, are counting units. Their number of atoms, number of molecules, number of moles. They are not measurements of mass. So the first thing we need to do is get out of the realm of mass and get into the world of moles. When in doubt, in chemistry in general, it's a good idea to convert to moles. It tends to be what allows you to bridge a lot of different concepts and calculations. So we're going to start with 26.9 grams of copper chloride. We're going to want to convert that to moles. So I looked it up real quick. The molar mass of copper chloride is 134.45 grams per 1 mole. So when I put that in the calculator, let me do that calculation real quick. Well, even if without a calculator, like I forgot we're supposed to be doing these without a calculator. So let me think. How would I look at this? I guess I could say that it would be like about 0.2, right? This is like 27-ish. This is about 135. So, I mean, it's hard for me to tell you how to do this. Let me see. Yeah, I'm just going to let you know that it's 1/5 and that goes to 0.2. Work on your mental math. You'll be able to do that too someday. Sorry, that's so unhelpful, but I don't want to go into too many details of other little mental math tricks. If you would have really had to divide it, you could. It would not take that much math to figure out that 27 goes into 135 5 times. Okay, so for the water, we have the 34.1 grams that we started with that did contain water minus the 26.9 grams when the water was gone. And that's going to represent how much water was evaporated and how much water was in our original compound. So that would be 7.2 grams of H2O. And now we're going to convert that to moles. So the molar mass of water is approximately 18.02. And what is that going to give us? That is going to give us an answer of about 2/5 or 0.4. Again, just some mental math. I don't know what to say. I just saw 7.2. Half of that's 36. And I know 36 times 5 is 180. So I kind of just made that jump in my head. Keep practicing your mental math. It's going to help. Okay, so what do we do now? We have 0.2 moles and we have 0.4 moles. So we're going to divide both by the lowest number. whenever you end up with fractional moles and you're trying to look at a ratio, whether that's like an empirical formula or something like this, impurity or hydrate, that's how you usually want to do it. So you get to whole numbers. That's going to be a 1 and that's going to be a 2, which tells me for every 1 mole of copper chloride, my compound, my hydrate, had 2 moles of H2O. So the correct answer, the correct way you'd write this would be CuCl2 with this little dot representing the hydration and 2H2O. So our correct answer is 2. So great job to everyone who got that. And even if you didn't, I'll admit the first time I did this, I rounded. I got real sloppy with my rounding in mental math, and I thought the answer was 3. So yep, answer was 2. Great job if you got it. Keep working if you haven't. All right, so we got another one that's a little bit more calculation intensive. This one looks like a combustion reaction. So if you aren't familiar with combustion reactions, well, we're going to review them a lot in week 4, but you should hopefully know a little bit about it. Essentially, especially when we have a hydrocarbon, we have some kind of molecule. In this case, we have one with carbon, hydrogen, and oxygen. These problems usually have a carbon hydrogen molecule. To be honest, the AP level, they like to get spicy and throw in an oxygen. And I've even seen some, we'll look at one at the end of class today, or the end of this video, that has a nitrogen. But this one's just a CHO. We don't know how much there is of each one. It's combusted in oxygen. That's essentially what combustion is. And what you get is CO2 and H2O. All right, cool. Now, how the heck are we going to use all this information? Okay, well, it told us we had a 30-gram sample initially. So we had 30 grams of this, and we had 44 grams of this produced and 18 grams of this produced. So real quick, I'm going to convert this to moles, which is going to be 1 mole. I'm going to convert this to moles. This is 1 mole. I'm not showing the work, but essentially I would be doing a molar mass conversion. And this one, I don't really know how many moles this is because I don't know the coefficients yet. All right, so you're like, how do you solve this thing then? How do we figure that out? Well, let's go and see where our elements are going. So in this case, we want to use the idea of the law of conservation of mass. We are going to mass this time, although we did convert to moles. We'll be using that as well. So in terms of mass, all the carbon that was in this compound ended up in that compound. And let's see what else. All of the hydrogen in our initial compound ended up in this compound of water. Now the oxygen got a little bit hairy. As you can tell, it was in 2 places to start with, and it's in 2 places at the end. So we're not going to worry about that. The question's not really focused on that right now. Okay, so that means that of this 44 grams, however much of its carbon is the same amount of carbon that was in here. So I can break that down real quick, and by doing a percent composition. So I know that the molar mass would be, well, let me think. How else could we do this? Maybe a little bit more efficient. Okay, so I have 1 mole of the compound. So if I have 1 mole of CO2, that also means I have 1 mole of carbon, and it means I have 2 moles of oxygen. So how much of this mass is carbon? It's going to be 12.01 grams of it is carbon. That's coming from the CO2. Now let me look at the H2O. I have 1 mole of H2O, which means that I have 2 moles of hydrogen and 1 mole of oxygen. So what's the mass of 2 moles of hydrogen? Well, it's approximately 2.02 grams of hydrogen. All right. So now we know about all the carbon and hydrogen, the masses. So in this original compound of 30, we can subtract the 12.01 and we can subtract the 2.02, and we will be left with approximately about 16 grams of oxygen. So I know that 12 grams of carbon is 1 mole. That was literally like what we got from there. I know that 2 grams of hydrogen is 2 moles. And I can check the molar mass of oxygen to quickly see that the amount of moles of oxygen would be 1 mole. So the best answer would be something like C, H2O. And when I look at my answer choices, there it was. So that's how you would solve this one. Again, this shows you how the more AP style questions, they bring in multiple concepts at once, such as what is a combustion reaction? Do you understand the law of conservation of mass? Do you understand molar mass? Are you able to look at a chemical formula and understand the ratios that it represents? So again, I like this question because it tests multiple concepts. This is the kind of thing you should get used to looking at. And again, I was able to do this whole thing without a. All right, I think this is the last of our multiple choice ones. This one was supposed to be pretty easy. I'm sorry if it slipped you up, maybe because it has like an A and a C and then it goes A and C. Maybe that's what happened here, or maybe you just misclicked or something. But this is basically a simple representation of something called a single replacement reaction. And this is usually done with some kind of binary compound. oftentimes ionic, usually ionic, and then some other ion that has essentially more affinity for the anion or vice versa. So we see here we had a binary compound, AgCl, exposed to potassium. And what we get is silver by itself and now KCl binding together. So I always think of single replacement as like C's coming in here and stealing B's girl. He's like kicking him out and says, I'm taking your spot. Or his guy. I don't know. You know what I mean. But yeah, let's keep rolling to the first free response question. Now, this is just like a little baby bit of a free response question because there aren't too many we can complete based on the material we've covered thus far in the course. I'm going to color in these nitrogens blue while we look over the problem. So the problem is describing a chemical reaction as modeled at the top. So that's our balanced chemical reaction, which shows us, hopefully you understand the mole ratios of the elements involved. And what the question is asking you to do is, what did the reactant mixture look like if the products look like this? So the first thing I identify, I'm expecting to see 2NO2 over here, and I'm expecting to see 2NO plus O2 over here. What I do see is that I have 1, 2, 3, 4 NO2s, and I also have some leftover NO. Yes, that's what these ones are for. These ones are leftovers. So that should be assigned to you. Oh, this is a limiting reactant question or an excess reactant question. It's not that the reaction started going backwards in equilibrium or anything crazy. You know, it's like go with like the more simple option. I don't see any equilibrium arrow here. That's not what's happening. So it appears what's happening is that the reaction went to completion, but there was some excess reactant. The other thing we want to consider besides identifying the excess reactant is that there are 4 NO2s, not 2. So 2 times 2 is 4, which means I need to multiply everything on this side by 2 as well. So I'm going to end up with 1, 2, 3, 4 NOs from the stoichiometry, and I'm going to end up with 2 oxygens. And then I still have to account for the 1, 2, 3, 4 excess reactants. So it's going to look something like that. All right, and there you have it. As you notice, this is one of the newer questions from 2018. They really like to put particle diagrams and conceptual stuff like this, basically having you use models and representations in multiple ways. So be ready for that. You'll notice when we look at an old AP question, because it's much more process-based and calculation-based. Okay, so good job if you got this one. If not, again, review it, practice it. If you need more of these kinds of examples, let me know. I can give you more types of particle diagrams like this in case you didn't practice them too much in class. All right, finally, here's the big kahuna of the whole assignment, and it's not actually that involved. It is a real AP question, but it's from 2006, and those are simpler times when the test was less of a thinking test and more of a memorizing test, I would say. Okay, so what are we going to do? We are going to figure this out. So if you were in class, you would have realized that we did do this one in class. This is basically like a molecular formula, empirical formula, percent comp style question. And I think there was maybe additional parts since it does say A, but this is what we're looking at for what we know so far. So the gives us some information. We have a compound containing CHNNO. When a 1.2359 gram sample is burned in excess oxygen, 2.241 grams of CO2 is formed. The combustion analysis also showed that the sample contains 0.0648 grams of hydrogen. Okay, so they gave us some information. First thing I noticed is that this is a combustion reaction. Again, if you're not familiar with that, we will be reviewing that during week 4, but you should probably know it before then. So the thing about combustion reaction always involves oxygen with some type of hydrocarbon, possibly with other elements mixed in, and it's always going to produce H2O, CO2, and in this case, it's also going to make nitrogen gas. But even if you didn't know that, you can complete the rest of the question just based on the H2O and CO2 data. So it says, determine the mass in grams of carbon in the 1.2359 gram sample of carbon. Well, we do know the initial mass of the CO2. It's 2.241 grams of CO2. And what I do know is that in 1 mole of CO2, there is 44.0 grams of CO2. And in that 1 mole of CO2, there is also how much carbon? 12.01 grams of carbon. You're like, that's all I have to do? Yeah, there's other ways you could do it. You could technically figure this out as a percent comp and then multiply it by that number. But a lot of times you can do much simpler calculations by simply letting the units kind of guide you. And since these are equivalent, right, that we know that it's true that there are 12 grams of carbon in 44 grams of carbon dioxide, this equation is just basically multiplying this number by 1. So what do we get? I don't know. I got to put it in the calculator. So this is an FRQ, so we should be able to have our calculator here. And it's going to tell me that it's going to be 0.616 grams of carbon. Okay, so that's our answer for part A. That's how much carbon we have. I'm going to write it again because we might need it for the next question. All right, so let's move on to part 2. When the compound is analyzed for nitrogen content only, the mass percent of nitrogen is found to be 28.84%. Determine the mass in grams of nitrogen in the original 1.2359 gram sample of the compound. Okay, so this is a basic mass percent comp. We did this kind of a problem earlier in the homework, but we did it the harder way, the backwards way. So now we're just multiplying our mass times our mass percent, and we'll get our answer. This one's nice and easy. 0.3564 grams of nitrogen. All right, let's get it. Okay, so, oh no, I'm revealing the answer already. That's okay. So when you do go over FRQs, I personally, and when I'm helping students as well, I always like to look at the actual answer key, not just to know like, oh, what's the right answer, but to see how they grade these things. Like this is what they were for. So in this case, the mass of oxygen, which we're trying to find, is going to be equal to the sum of the whole compound minus, the total of the whole compound minus the sum of all the other elements, which they did tell us. A lot of people miss this because they read it quickly the first time, like, how the heck am I supposed to know the hydrogen? Well, they gave it to you right there. That's how you should know. All right, so 0.0648 grams, that's our hydrogen, plus our, what was the original one, 0.6116 grams of carbon, plus the what was it, 0.3564 grams of nitrogen. And when we do that calculation, we are going to get 0.2031 grams of oxygen, as the answer key says down here. Now, why did I leave this one on here? Now I remember. It's because of this, where it gives you this data. So it was only 1 point, but they said the answer must be consistent with part 1 and 2. So even if you screwed part 1 and 2 up, but you still effectively use those numbers in part 3, you could still get this question right. So that's my encouragement to you. If you feel stuck at the beginning of an FRQ, keep on pushing. You might be able to answer some of the later parts. You won't screw everything up because you screwed up part A. So don't approach it with fear, approach it with confidence. Now, if you don't know what combustion is, yeah, this problem would probably be pretty hard. If you don't know what the law of conservation of mass is, probably pretty hard. But if you just make a small calculation error, don't freak out. You can still get most of the question right. Okay, and the last one, number 4, I had to leave some extra space for this. This one is all about determining the empirical formula of the compound. So how are we going to do that? We practiced it a lot in class. Now, in class, I told you to essentially assume you have a 100-gram sample, and that is the best method when you're only given the percent comps for each of these. But we actually know the amount of grams. We don't have to use some assumed compound or with mass comps. So we have 0.616 grams of that. We have 0.0648 grams of that. We have 0.3564 grams of nitrogen, and finally 0.2031 grams of oxygen. So how do we do these again? Oh yeah, that's right. We need to convert to moles like we always do when we're not sure what to do next. So we know that 12.01 grams is 1 mole. This guy's going to be what? 1 mole times 1.01 grams. This one's going to be 1 mole times 14.01 grams. And finally, oxygen is 1 mole over 16.00 grams. All right, so when we plug all those into the calculator, because yes, this is an FRQ, so we would have access to our calculator, it's 0.5092 moles, and we get 0.06429 moles, and we get 0.02544 moles, and we get finally 0.01269 moles. Okay, dude, we can't just write like carbon 0.5092 and hydrogen 0.06429. Nope, you're right. We didn't screw up. This is all, everything's good. Don't freak out. We are going to divide all of them by the lowest number of moles. This will effectively, hopefully, if we're doing everything right, turn everything into whole number amounts. At the very least, it's going to turn oxygen into a whole number, right? Because anything divided by itself is 1. So what do we get when we plug these in? All right, it's close to 4, but it's actually a little bit off. 4.013. This is 5.066. 5, and finally 1.000. So be comfortable with rounding these off. That's a 4, that's a 5, that's a 2, and that's a 1. So when we put all that together, what are we going to get? C4H5N2O. And that would be our final answer. So great job if you got through all those. Hopefully this video was helpful. I'll try to make one each week. And that's why it's really important you turn in your homework by Thursday night so that I can see what questions we're struggling with and I can make sure these solution videos get posted in time for you to check them out and figure out what went wrong as well. All right, so thanks for making it through this whole video or making it through just the chapters you needed. Either way, I don't really mind. If you did find it helpful, like and subscribe. If you didn't, let me know how it could be better. If you're struggling with anything in AP Chemistry and you feel lost, overwhelmed, and you just need a little bit of extra help or support, feel free to reach out and I will see whatever I can do to help you at an individual level. Chemistry doesn't have to be super draining or super difficult. It can be actually sort of fun and like a puzzle if you approach it with the right mindset. So hopefully that uplifts you a little bit. Keep on studying. We've got about 7 weeks to go. Yeah, and have a great night. Thanks for tuning in.